science like there's no tomorrow.
Hi everyone, welcome to the third block of lecture number 2 of Financial Engineering course. Today we will continue with our journey on filtrations, conditional expectations and measure changes. In today's block we will mainly focus on measure changes, and also there will be a homework exercise. So I prepared a number of exercises that you can practice and see whether you understood materials covered in today's slides. Let's take a look at the content. So in the first block, we had filtration, conditional expectations, and some exercises in Python, simple exercises in Python. Second block, we covered pricing using conditional expectations. So we used a Black-Scholes model extended with a stochastic jump volatility, and I showed you how to benefit using conditional expectations to improve the convergence. And we also started the talk about the concept of a Numeraire and measure changes. Last lecture, or last block of this lecture, we finished with measure changes, where we changed the measure from the measure P to measure Q. The concepts of measure P and Q we already have discussed in the lecture in the course of computational finance. So if you like to refresh, I recommend to follow that course first. Today we will concentrate on applications of measure changes. So it will be applications of a Grzelak theorem, which was covered also in the previous block. And today we will define the concept of a stock measure. We will also use measure change to reduce the dimensionality, and very importantly I will also show you how to define a T-forward measure and how to benefit from measure changes once we want to remove stochastic discounting in equity or even interest rate products. And I will finish this lecture, this 3-block lecture, with a summary. So I will conclude with I'll give you some details of what we have discussed. It's a refresher, and also I will give you a number of exercises as a homework. I hope you enjoy it, and enjoy the course. Now, let's take a look at the problem, which surprisingly the measure change will be very beneficial and will simplify the problem significantly. So in this case, we have again Black-Scholes economy. So this is already defined under the risk-neutral measure theorem. So we have the interest rate R, money savings account, also with R, everything is well defined. We are looking at the price of the following derivative. So at the maturity, the expiry of this option, so we have a payoff, which is maybe unusual payoff because it pays us square of ST minus ST times strike, then it's a maximum of 0. So of course, if K becomes large, this value can become significantly larger than this. This could be then a 0 value, of course. So if you look at the analytical solution, it's a bit problematic here, because if we look at the distribution of this quantity S squared minus S, in both cases we are dealing with a log normal distribution. So ST is log normally distributed because it's just geometric Brownian motion. And now we have S squared minus S. So in essence, we are looking at a sum or difference of two log normally distributed random variables. And we know that we don't know properties, we don't know distribution for difference or sum of log normally distributed random variables. That makes this expectation or the pricing rather difficult, right? Of course, we could just calculate this expectation, because we know in both cases we have a density of stock. So we could calculate this integral as we could do in the case of a Black-Scholes case. We would arrive at some formulas that definitely would be a possible way out. However, here I'd like to show you how by measure change you can solve this problem in a very, very elegant way, and a way that actually will be equivalent as you would just directly integrate this expectation using the density, log normal density for S. So, okay, so let's take a look at this equation. So the Numeraire right now is MT, so it's a money savings account. we have a stock squared. So you see that essentially, if we divide now everything by MT, we don't really can benefit from it, right? Because those MTs are nowhere here. However, we could also see that if we would benefit, we could divide all those terms in a maximum by ST. We know that ST is non-negative, so it's not a problem if we divide everything out. We could actually simplify it, because then we would have ST minus K, which is something we could we know how to handle, especially if it's in a log normal process. So you can see that now we divide our Numeraire is a money savings account, MT, and preferably one that we would like to have is ST. So that suggests that we would like to switch from the risk neutral measure Q into the stock measure S. So we want to change the Numeraire from the risk neutral measure associated with the money savings account. We want to switch to the measure driven by the stock asset. And this basically means that in the Black-Scholes world, right now we have this quantity that ST divided by MT is a martingale, right? Because once we switch the measure to S, this is not the case anymore. So this quantity won't be martingale. Then we will have MT over ST. It's a martingale, because then money savings account will be expressed in terms of stocks. I can imagine this could be a little bit of counterintuitive, but this is the technology. We choose an asset. So actually, maybe it's counterintuitive because everyone's got used to it so much that money savings account is always the Numeraire. Think about it from the wider perspective. You can choose an asset that you would like all the assets in your portfolio to correspond to be expressed in that unit. So stock is obviously also a candidate here. So okay, so we have a plan. We would like to switch measure from risk neutral to the measure associated with the stocks. So let's do it. So first step is that we will apply the Rodom-Nikodym derivative. And this derivative we also have seen in Gibbs-Anoff theorem, where we were looking at the ratio of two measures. So Gibbs-Anoff theorem shows us how to switch between different measures. If you have measure A to measure B, what type of Rodom-Nikodym derivative we need to derive. Of course, here it is kind of mechanic how you can do it. I'll show you. So we first write the ratio of two measures. It doesn't matter what order, because we can always divide out. So we can always switch from here. We can always go to DQS. So it doesn't really matter what ratio we choose. Here, the principle is as follows. If you have a numerator with S, then you always start with an associated asset. So here it's numerator is S. Always take asset at the maturity. Then always divide by asset in the beginning. Then you have the other side, which corresponds to the other asset. You do exactly the opposite. So the first one is initially, then is maturity. So it's basically very simple. So the first will be match. The nominator is always associated with the payment at the end divided by beginning. And then the second term, it's opposite. So we have a money savings account in the beginning divided by money savings account at the end. Now this is kind of intuitive. I always follow this strategy. So whatever is a nominator at the end divided by initial, then opposite falls for the other asset, which is here in the other Numeraire. Okay, so this quantity, of course, here we can actually, by multiplying everything by dq, we can have a ds, or dqs is equal to actually we can slightly different, so of course st over st0 times mt0 divided by mt times dq. So this is basically the connection between the measures, how we can switch from one to another one. Let's take a look at the payoff right now. So we have expectation under Q. This is the payoff we have seen in the previous slide. We can also write this expression, this expectation, as the integral over 1 over m, and then we have a payoff function, and then this is equivalent with a dq. So this expectation and associated measure corresponds to the dq. And of course, dq, you can see this is dq, it's a measure which is here. So we can essentially find out what dq is from this expression. The substitute. Of course, then you substitute with would be inverse. So we have a st0 divided by st, and then we have an mt0, mt divided by mt0, and then this substitution gives us this term here. So substitute this, we get this term. Of course, now we can also simplify, because this is simplified, because also this is MT here. So this goes away with this. This is constant. This is also constant because it's at MT0, but T0, so it's initial time. Those two terms can go outside. And if we go back to the expectation, this is the term we get. Yeah? So this is actually 1. So this can cancel out with this. Then ST can be used, can go under the maximum, because it's of course non-negative. We can divide everything nicely out. So then we get rid of it, of the square here, and then we have only strike, and only one part, which is here. We have only the ST0. So this is, I think I derive it here. So you see, after simplification, we end up with this term, and then of course this is also known, so this can go outside. So now the value, you see the value at time t0 is given as a expectation under measure S of a maximum st minus k0. And this is also constant. It's actually, this is even 1, because manisim's account, initially it is equal to 1. So we only have a st0 multiplied by this expectation. Of course, now the question is, okay, this is half of the success. We already know that the payoff is simplified. It's very good. But of course, the bottom line question is, what is the dynamics of ST under the new measure? Because if, for example, the dynamics of ST is not anymore log normal, but it's much more complicated than we started with, then we are not actually solving any problem. We make a problem just somewhere else. So if, for example, because now, if we have this expectation, every stochastic differential equation, every asset, every stock, which is here, every random variable, every process, has to be defined under this measure. We cannot just take the dynamics of ST, as we have defined in the slide here, and substitute there. So that would be really a mistake, because you see that this Q does not, it should be QS, so it has to be changed to the measure. So in order to actually benefit from this expectation, we still need to change the dynamics of process S to be under the same measure. Otherwise, we cannot really apply that. Of course, now we already have discussed what the quantities are, the martingale. So everything divided by the stock process, it has to be martingale under this new economy. This also will help us what exactly the measure transformation, how it looks like. The discounting process, this is the question, we discount everything with stock. So stock is our numeraire. We discount all the assets in this economy with stock. Does it make any sense? Yes, but only if we have a stock, the changing measure, if the stock is, the dynamics of the stock is simplified, is not worse than log normal, so it's nothing, let's say, so whatever, it is still log normal, or it's something similar of the dynamics that we can use, for example, using Black-Scholes model, then indeed, then it's benefits. Otherwise, there is no benefit. But of course, since I'm showing you in this particular example, I'm pretty sure you're already expecting that there will be a benefit. So let's see us further why there is where exactly, what is the dynamics of S under the stock measure. It's also, you have to get used to it. We talk about the stock dynamics under the stock measure. So the question is, how to get it? Is it only S divided by S? This is the dynamics we are looking at. Of course not, because this would be just 1. So even if you do the dynamics, this is 0. So there's no dynamics. However, if you look at the dynamics of MT over dST, that indeed that can qualify to give us the hint, give us the measure transformation that we need to use to find the dynamics of ST under measure Q. Under measure S. In measure Q, we already have it. Okay, so let's wrap up what we have learned, what we know about the process S under different measures. So QS is the measure we discount all the assets in this account. So money savings account, stock, everything is discounted with a stock at the numeraire. We also know that MT under this new numeraire, or ST, DMT ST, needs to be martingale. Therefore, we expect this kind of dynamics. This is something already from the previous example. If a ratio of MT ST is a martingale, and we know it is martingale, then there should be no drift. And we also have Brownian motion under the new measure, but we just don't know yet what is the variance, which is the volatility of this process. And this is actually what we need to find out. We need to find what is the term here by the volatility, and also what is exactly the measured transformation under this new measure. Okay, so we look at again the same as we had for Black-Scholes case. We take a ratio of a money savings account over the stock, apply ITO, substitute all these processes we know for the stock process, for the money savings account, simplify, and then we arrive at the following expression. So we have, of course, this will be canceling out with this term, right? Then we have, so of course we have only the dt term is this element here, which we can substitute here. And then we have a minus, and then we have a volatility part, sigma TST dqt. Okay, so of course we know that MT over ST, in this case, is not a martingale, it still has some drift. And we see also the volatility term. This is the sigma MTST. What we will do right now, we will just follow exactly the same procedure we have done for the Black-Scholes case. This means that we expect the new process under measure S will be dm dmt divided by st would need to be driftless and would need to have exactly the same volatility structure as the process under the Q measure. So this is the term that we have from here. So we put on the left-hand side, we put this term here. On the right-hand side, we put what we expect to have, because by definition, we know that MT over ST has to be martingale. So of course, this process is driftless. We know exactly how the Brownian motion part by Brownian motion will look like. So we, of course, again, as before, those terms will cancel out. And this is the measure transformation we arrive at. So you see, we have used the Grzelak transformation, but we haven't applied the theorem directly. But because we know that the processes satisfy a number of conditions necessary to be used for the satisfied conditions that are allowing us to use the Grzelak theorem, we can actually imply measure transformation from the properties of the processes. And this is very powerful and extremely handy way to derive measure transformation. Okay, let's go further. So of course now, since we know the dynamics, so because we know this process, how it will look like, we know the measure transformation, we can now substitute this, of course now we substitute this Brownian motion dwq to the dynamics of the stock process under measure Q. So this is basically the substitution. Of course we take sigma dt on the other side, and then we arrive at the dynamics of the process S under measure S. So you see, luckily, the process didn't get more involved as we were afraid of. The process is still log normal. But something funny happened, that our drift, so our for interest rate, now we have also extra element for volatility. This means that there is this correction actually comes from the ITO, comes from the measure change that will allow us to switch from measure Q to measure S. And this is a quite important element. If you implement both processes under Q and S, you have to make sure that those extra drift corrections are there. And of course, the last step, we have to assess our expectation. So finally, once we know the dynamics of S, so we know the dynamics under the S measure, this is this dynamics, we can use these dynamics to evaluate the expectation under the S measure. So now the dynamics from the previous slide, we can substitute here. We can use that solution for that S in this expression, and then we can find the expression for the option price. It is very similar as we could just have for Black-Scholes case. However, you have to make sure that you have extra coefficient sigma squared in your Black-Scholes formula. And also another element, please don't forget about S0 in front of the expectation. This also came from the measure transformation that we have used. So you see, if you like to solve this complicated expression, essentially it collapses to a simple expression with one log normal process. It's very interesting. So we had a difference of two log normal stocks. It was S squared. So the original payoff was S squared minus S. It was a sum or difference of two log normals. After measure transformation, the problem becomes expectation of a single log normal process under measure S, where S the dynamics of S is still log normal. So you see, it's a very elegant, very beautiful way of deriving the pricing. Here you can just directly use Black-Scholes formula with extra scaling of zero. So this is extremely powerful, extremely elegant. In your homeworks, at the end of today's lecture, your assignment will be to compare the solutions that we have obtained here with a standard approach. So then you can actually verify numerically whether what we have done so far, these derivations, we haven't made any mistake in Monte Carlo simulation against the analytical expression. Now, let us increase the complexity of the pricing problem and let's take a look at the high dimension problem. So now we consider a two-dimensional system of stochastic differential equations. So we have two stocks, S1 and S2, defined under the risk-neutral measure Q. And those processes, so the two Brownian motions, they're correlated. We already have discussed in a course of computational finance how to correlate Brownian motions and how to deal with those simulation of those processes. So if you are not familiar, I would refer to the computational finance course. And the payoff of our interest is the following. So we have a payoff, a value today. It's given as the expectation under the risk-neutral measure. This is associated with the money savings account. And then we have a kind of interesting payoff. So a payoff pays us amount of S1 stock at the maturity of S1, but only if stock 2 will reach certain level. So only if at time T2, at time T, stock S2 will be larger than a given strike, then only we receive this amount S1 T, so stock discounted to today. Otherwise, this payoff is equal to 0. So it's an interesting case because as you can see that in order to calculate this expectation, we need to have a joint distribution between these two stocks. So of course, somebody could argue under the log transformations, we still have a kind of a normal distribution. So it's e to power x1, e to power x2. And then you can maybe solve this integral analytically. And actually, this is possible to solve this analytically. However, I will now show you how to use measure transformation to get this expectation in a very elegant, again, as previously form, using the Grzelak theorem, using the measure transformation. So let's take a look critically. What is the asset that will be the best candidate to be our numeraire? So of course, we need to change from the money savings account. We cannot really change to S2 because S2 is this indicator function, so that's not really helpful. Of course, S1 is the one that you would like to choose. So the approach here is to choose measure Q to measure Q as 1. But of course, our economy is now bigger because previously we had economy consisting only of two assets. We had money savings account and also we had a stock. Now it is much more complicated because we have three assets. We have a money savings account, so this is money savings accounts defined here, and we have two stocks. So we have economy consisting of three assets. So this basically means that not only stock money savings account divided S1 needs to be martingale, also S2 divided by S1 has to be martingale. Let's see if we can step by step derive all the necessary measure changes. Of course, we also have additional complexity here because Brownian motions W1 and W2 are correlated. So let's see how this will impact the change of measures and also how this correlation effect, correlation between Brownian motions will be included in the dynamics. Essentially, we would expect that this rho should arrive somewhere in the measure change. If it didn't, very likely we haven't done the measure transformation correct because then the relation between two Brownian motions and the different measures will be impacted. Okay, so like we just discussed, the S1 is the candidate to be our numeraire. Step number 2, once we establish which of the asset is the candidate, it's the best candidate for being a numeraire, we have to find out the Radon-Nikodym derivative. Of course, this is necessary element for Grzelak transformation because it allows us to see how this payoff, because we have a payoff under Q measure, this payoff will look differently under S1 measure. So of course, first we need to find out how this payoff looks like under the new measure, and then we can apply measure transformation to find the stocks and also money savings account under the new transformed measure. Okay, so as before, we have S1, so S1 at the maturity, at the time t, divided by initial, and then we have an opposite, we have an MT0 divided by M capital T. This is our measure transformation. This is actually the Radom-Nikodym derivative. If we look at the dynamics of it, basically that will give us exactly the measure change that is necessary for the descent of T. Of course, our approach, we are really pragmatic. Our approach is to find out measure change given the martingale properties that need to be satisfied in our world of derivatives. So, okay, so first step, as we did it before, we need to find out what is the payoff, what is the expectation under the new measure, where we can actually see the improvement, where the payoff simplifies. Of course, that's the first step, because if the measure change will not simplify our payoff, then what's the point, right? Because then we could actually, if the payoff stays complicated, but we have slightly simplified processes, that may be not so much beneficial. So first we need to verify whether the measure change actually simplified our payoff. That's the crucial point here. So after substitution, as we have done before, we have the following expression. So we have ST1, MT with indicator. So this is everything what we had before. And now we have the part which comes from the Radom-Nikodym. So this is the part which comes from this change. Of course, now we substituted for dq, we substituted dq as 1. So this basically goes here, and then everything is inverted, right? Because we have to find out what is the formula for dq, and then we end up with dqs. And this term here would be essentially a fraction, which is an inverted fraction, which is here. Okay, so then we substitute this to expectation, and this is what we get. So here what we can see immediately that this will cancel with this, so two money savings account will cancel. Then the stock here will cancel with this one. This is really excellent. Then we have ST0, MT0. This, of course, and those are measurable because we know it today. They can be taken outside of the expectation, and even further, this cancels with this. So we only end up with a stock S1 at time t0, which is deterministic. And we only need to find out what is the expectation under measure S1 of indicator function S2 at capital time t bigger than strike. And of course, we know that expectation of an indicator is equal to probability that the event in the indicator is satisfied. So basically here we have a QS1 probability, because we see, so this is actually probability under this measure that S2 is bigger than strike. So of course now, as we have seen it before, we need to find out what exactly is the dynamics of S2 under the new measure. We need to find this probability under the corresponding measure. Of course, strike stays the same. So and this QS1 is associated with the new measure with where the numeraire is S1. Of course, so as before, we need to make sure that all the quantities are martingale. Martingales are transformed, their measure transformed to the new measure, which is measure QS1. Okay, so the first quantity we take is the money savings account divided by the quantity S1, the stock 1. And again, we apply Ito's lemma, we end up with the dynamics. And as we just did it already multiple times, we know that under the new measure, S1 measure, this quantity under the S1 measure has to be martingale. So we have, it has to be driftless, and the volatility coefficient will not change. So essentially this has to be equal to MT S1T. And here we have it's a minus sign in front, a sigma 1 dW1. And here we have S. So this is the first transformation, of course, then everything nicely cancels. And this is the term we have for the measure transformation for the first process. Of course, as you can see now, the correlation element that we even discussed is not even playing any role here, because MT is deterministic, so that's not really having any value. very interesting case will be once we have S2 divided by S1. Then we really will see some relation impact, which comes from the ethos table, which will be related to ethos table. So, okay, so this is the first measure transformation. So once we substitute this Brownian motion for the first one, we already know how the dynamics of S1 will look like under the S1 measure. This will be some additional correction in the drift. So after substitution, as we did before, then we have, this is the dynamics of the process S1 under the S1 measure, and there's this extra term we have right now in the drift. So it's still log normal process. You can see you can multiply both sides by S1, so it's still log normal, nothing has changed. For the second stock, so of course now we have a little bit more work. I recommend you can do it yourself, but what we are looking at the ratio S2 divided by S1. So once you apply ethos lemma to that, and you will find the following dynamics. And this is kind of interesting then, because we have two Brownian motions now, we also have three terms. The first term will be a dt term. So this is something that we already expected because it's not a martingale. So this will be something we need to change. And we have two Brownian motions. The first one is for stock 2 under Q measure, and then we have a Brownian motion for stock 1 under Q. But before we just derived here in this slide, derive the measure transformation for stock 1. So we can simply substitute this dynamics for the Brownian motion into this equation here. And this is what we get. So we get W1 S1, and then this is the remaining one. So we know we cannot touch it anymore, right? So this is which stays, because this is already properly defined under the S1 measure. Only one thing we can change is the S, so W2 Q measure, such that this quantity will be a martingale. Maybe it's not necessary. Okay, so that can be done simply. This is done essentially the same way how we have done before. We equal it to the Brownian motions of the under the S1 measure, and we know that those quantities will be driftless. So this would essentially imply this term has to be equal to dt. So to basically has to cancel this dt term under the S1 measure. That basically means essentially that if we have this sigma 2, this will be divided by sigma 2. This means we have only left with a minus rho sigma 1. This is the correction term which we have here. So then under the second measure, the second process under the S1 measure, this will be the measure transformation. Its measure transformation comes indeed from the fact that we look at the S2 divided by S1. So if we put everything together, then we see that two processes, the S1 and S2, this is their dynamics under the S1 measure. So we have two drift corrections, and indeed in the process for S2, we have this additional correction which comes from the correlation. And this is basically, at this point, this is sufficient to find out what is the probability, because ultimately we need to find, sorry, this is here actually, we need to find probability of S2 is bigger than stripe. We have three constant parameters, rho, sigma 1 and sigma 2. This means this is still log normal. We can easily use the property of a log normal distribution to calculate that, that probability. And that would be the solution of our evaluation. So this is also very interesting. Maybe the biggest takeaway from this derivation in this case for the S1, once we have multiple variables, it is important that you order your variables from the simplest to the most advanced. So first one, we looked at the MT over S1, and only then we looked at S2 divided by S1. If you start otherwise, you can see that we would have this problem. We would not know what are the two unknowns. And because we use the measure transformation, which came from MT divided by S1, then we only end up with one equation and one unknown. And another takeaway, another important element that you could actually use that could simplify even further is that I would recommend that if you have stochastic differential equations as described here, I would always recommend to use Cholesky decomposition to express stochastic differential equations in terms of independent Brownian motions. Your correlation coefficient will be just immediately transparent in a SDE, so it will be this coefficient that will be in front of the volatility, in front of the Brownian motion. In that way, you will never miss correlation. Because once you move to independent Brownian motions, it's always very also elegant way of simulating, and also it allows you to segregate the processes from the easiest or the fundamental one, and then build up dependence accordingly. So this is my personal recommendation, and I would also, typically this is how I also do it. So here, of course, because it's log normal, we can find the distribution for it. It's very clear what the distribution is, just log normal with some additional correction, which comes from this term here, and that basically, yeah. So we have a drift which comes from here, and we have a half sigma squared which comes from this part. And this is because of the Ito formula if you apply to find a solution for S2. The final measure transformation of today's lecture is linked to the zero coupon bond. Zero coupon bond is one of the simplest instruments one can actually imagine in the interest rate world. And actually, it happens to be also one of the most powerful instruments once we talk about interest rate pricing. Zero coupon bond is a derivative which essentially we can see that here in the payoff we have initial time t0, we have some future time capital time t, and what this contract actually states is that at the maturity time capital time t, we will receive €1. That's it. Although very simple, although very straightforward, and actually it is one of the simplest ones available derivatives, it is extremely powerful because it actually constitutes the fundament of the pricing in the interest rate world. Zero coupon bond has two arguments, so we always deal with two arguments. It is t, representing actually current time, and this is the contract maturity. It's a capital time t. By definition, we always have this relation, so small time t is smaller than capital time t. At the maturity, we always receive 1. However, it can also happen that at the inception, the value of a zero coupon bond, it is bigger than 1. This means that there exists time where we could have situation where this is bigger than €1. And this is always related to the fact that there could be negative interest rate present in one. Of course, it doesn't mean necessary that there is somebody buying those particular bonds for negative rates. However, many interest rate derivatives, actually most of them, they can be decomposed in a sequence of zero coupon bonds, always related to zero coupon bonds. This means that if we look at these fundamental blocks, let's say there is some complicated derivative, which essentially has a negative rate. This essentially would imply that those ingredients which are used to build this particular swap or other derivative, that those zero coupon bonds have a rate which is negative, and that implies value bigger than 1. One can ask why there is even a case where why the net rates are negative. It could be related, for example, to the interventions of central banks that they would like to increase the liquidity in the market or enforce banks to issue more loans. And by making rates negative, the expectation is that people will spend their money sooner, and that will stimulate the economy to some way. Whether it's true, whether indeed people will spend money once the rate is negative or not, that's a different economical, let's say, discussion. From financial engineering, from the pricing perspective, negative rates, it's reality. In the past, essentially models that allowed for negative rates were criticized. And now actually this is a standard. So model which does not allow for negative rates, this is the one which is criticized. So zero coupon bond can be also associated as a numeraire. And we will see in the follow-up lectures, I will spend a lot of time on changing measures where the zero coupon bonds in particular are used. Of course, not necessarily. We will not always change measure using zero coupon bonds, but you will see that zero coupon bonds are a very important ingredient of the whole process of changing measures in the interest rate walls. Some maybe more details about zero coupon bonds, and also I'll show you how this Rodom-Nikodym derivative looks like. So zero coupon bond, once we change the measure to the forward measure, forward measure is always associated with this zero coupon bond. So this is the ingredient, this is our numeraire for changing measure from risk neutral from some other measure to the T forward measure. So this T is always associated with the payment of a zero coupon bond. Like I just mentioned, this is the very simple product which has a payment at 1. From the fundamental pricing theorem, we can actually see the current value of this product, of the zero coupon bond, can be derived from this generic class pricing equation. So the generic pricing equation, we see that we have an expectation of a discounted, so it's of course the stochastic discounting here, and we have a payoff. In case of a zero coupon bond, this payoff is equal to 1, so I'm going to substitute. Then we have equation for zero coupon bonds under the stochastic interest rates. Of course, stochastic interest rates, it is necessary to have them once we talk about zero coupon bonds, because zero coupon bond is a product which is interest rate related. So if you would have a deterministic case, so you would say the rates are deterministic, this basically means that there's no really asset class, because everything, if it's deterministic, there's no uncertainty, there's no stochastic differential equations to model the uncertainty. So once we talk about zero coupon bonds or other interest rate products, always keep in mind that interest rates in that case are not deterministic, they are stochastic. So in the examples today, we had interest rate, for example, in Scholl's case, the interest rate was constant. We had also a multidimensional set of stochastic differential equations. There also we have seen the interest rate was constant. But once we move to the interest rate wall, where the numeraire is related to the instrument from the interest rate asset class, then the assumptions about interest rates is not anymore that they are constant. They cannot be deterministic, they have to be stochastic. And this is the pricing equation. This is, we will all more often see this kind of equation for pricing of zero coupon bonds. So we have an expectation, and we have integral from from today until the maturity of some interest rate. This will be discussed in the follow-up lecture, how this interest rate can be built. And then we have filtration. Of course, filtration corresponds to today's date. We have a final value of equation. How does it look like? How does Radon-Nikodym derivative look like? Again, we follow exactly the same strategy as we have done for stocks. So we have a zero coupon bond at the maturity divided by the value today. Then we have an opposite for the other side. So money savings account initially, money savings account at the end. Then the pricing equation, how it changes from the risk neutral to the T forward measure is as follows. We again use the Radon-Nikodym derivative. We substitute for dq. Now, of course, this will be an equation for dq. And then we have dqt, so the forward measure. And then we have, of course, money savings account will cancel out. So this stochastic discounting, this money savings account is defined as E from T to T, of course, T0 or S ds. So this is done. That's typically very beneficial, because when you look at it, this payoff, so it's h, here if you have h multiplied with some divided by money savings account, then if this asset inside is stochastic, also of course, then we need to have a joint distribution between integral of interest rate asset which is there. So obviously it's very beneficial to use zero coupon bond to change measure to remove the stochastic discount outside the expectation. So of course here this will cancel out. This is equal to 1. Zero coupon bond at the maturity by definition equal to 1. This is also deterministic, so actually it's cancelled out of this. So we end up with this expression. So what we see here is that because we have changed the measure from risk neutral to T forward measure, stochastic discounting that we would have under the stochastic interest rate world, this is what the assumption here is, then we simplify because we don't need it anymore. We can actually work with a payoff under the T-forward measure. So the discounting, stochastic discounting is gone. And this is also, you can consider this as an example of a case where we have reduced the dimensionality, because our problem from two-dimensional, for example, if here is HT would be, for example, as an example, let's say call option ST minus K0, then you see that in order to find this expectation, we will need to find distribution of ST and discounting. All this, we have joint distribution between these two elements. Sorry for my handwriting. This is actually, again, let me rewrite here. Maximum, here we have a S capital T minus K0. So if the pay of H would be of this form, then we will need to find joint distribution between S, which is here, and the discounting, which is here. And of course, under the stochastic interest rates, this is not deterministic, then this joint distribution can be rather involved. For example, here you see that if we have some interest rate, which is CIR or some more complicated short rate, this distribution joint density is not even known, or it's very difficult to get. By changing measure, we can actually work with a payoff. We can price under the T-forward measure where the discounting is good. It's very, I would say, this is a super elegant way of calculating pricing. The stochasticity from the discount factor is completely removed, because this element is actually deterministic. So it's a number that you can read in the market. Later, in the next lecture, we will dive deep into pricing using stochastic interest rates. Those relations, measure changes, stochasticity of discounting, I think it will become much clearer. Of course, we have around 13 lectures fully focused on interest rates. So you will get used to those measure changes. I'll be maybe repeating some of those elements, and I hope that you will benefit to really get use those measure changes techniques as very powerful tools in your daily operations, hopefully. Let us now summarize what we have learned today in this lecture. We started this lecture number 2 with a concept of filtration. I gave you quite some information how to think about filtrations, when things are measurable, when they are adopted. I related also the concept of filtration with traveling in time somehow. You have to put yourself into perspective of a time traveler who would like to, who cannot make a mistake, and he has to be always careful what he knows, what he doesn't know, and what it's certain, that's basically deterministic, at a given period of time if you travel in time. And this is something that we will learn more and more, especially in the context of XVA that will be covered later in this course, of HVAR, etc. This will be particularly important once we talk about, let's say, nested Monte Carlo, path-dependent payoffs, but also once you think about how my portfolio value would look like in the future realization. Realization is a scenario that you, for example, have simulated. Then it's very important that you know that, okay, if I have moved, let's say, 20 years ahead, what things at that point are known, how you have to rebuild your market information, and how to use them, for example, for pricing. So filtration concept is very important, and I hope that you understand now how to think about it, how to link the filtrations also to the conditional expectations, how to think about how to benefit even from the changing of the expectations, how to use the Stour property to get the benefits of the knowledge that you know. Is the case that the problem you pose, the problem you have to solve, it seems to be very complicated. However, for some special cases, the analytical expression, then combination of those filtrations, conditional expectations, would allow you to use that knowledge to facilitate, to improve your simulation and your numerical results. Conditional expectations in Python, I have shown you here. There were 2 experiments. The first one was about the simulating of a Brownian motion and how to do the nested Monte Carlo, how actually to calculate the conditional expectation conditioned on the filtration, which is in the future. It's not today, it's only in the future. It is actually also a very important element because that kind of concept will also pop up later once we talk about Kolbo exotics, once we have to deal with a Longstaff-Schwarz algorithms, etc. This may not be covered in this course, it will be in a follow-up course, but it is important to understand what filtrations, also conditional expectations, are. Convergence experiment. So this is also here we consider the option pricing using the Black-Scholes. We have conditioned jumps. I also have shown you how you can how the numerical experiment, how the convergence can be influenced by inclusion of the information that you have that you can include in your Monte Carlo simulation. Then we move to the concept of a numeraire. So this concept of a measure change. Which asset is tradable, how to choose a numeraire, and how this measure, sometimes you have those QTs by the Brownian motion, how this is related to a numeraire. This is kind of important. In time, it will be very natural for you to know which measure you're under. But if you see a Brownian motion, this is, I would say, the most important takeaway. If you see a Brownian motion, always ask, under which measure is that Brownian motion defined? Then you know you properly where your starting point is. Then you can actually go forward. If you don't know Brownian motion under which measure is defined, I even don't continue because that's basically you don't have enough information to proceed. Then we have considered quite a few examples of benefits of measure changes and how we can exploit, how we can apply the measure change, the Girzanov theorem and the Radon-Nikodym derivative for measure transformations. So the first case was, okay, let's apply measure change to transfer stochastic differential equations from measure P to measure Q. It was the case of Black-Scholes model. Later, I showed you how to change measure from risk-neutral measure associated with money savings account to the stock measure. Then we use also measure change for the dimension reduction. And then there was an important element when we used the T-forward measure, which was associated with the zero coupon bond. And that measure allows us to reduce dimensionality too, because we can remove the stochastic discount factor outside the discounting, which is stochastic, outside the expectation. And that also simplifies the problem. This will be also very beneficial later once we talk about multi-assets stochastic differential equations defined in multiple asset classes. And of course, now it's a homework in the summary of the lecture. So we have summarized, and now it's of course time for homework. I have prepared a few exercises. It will be often the case that you will see some exercises from the book, for which you can find the solutions on the website. And for odd solutions, the solutions are given. For even solutions, they're only given for the teachers. So please don't ask. I'm not allowed to share those. But then I hope you will enjoy those exercises. So exercise 1.9 is to find some expectations. So we have a process of rather complicated form. Your task is to find the following, the expectation. So we have e to power t to t, wt, and we have to show that this equality works. So it's a bit technical. Of course, in this course, maybe this is not related to very much to the content per se of the measure changes, but you have to keep in mind that in order to be fluent in derivative pricing and also in interest rate, you really have to have, let's say, upper running skills once we talk about martingales, measure changes, and also Ito differential equations. So Ito has to be essentially your day-to-day operation. You have to get used to it. So this is exercise 1.9. Then if we have a 1.2, you have a differential equation, and you have to find the dynamics for certain processes. So this is a process where we have gt is s squared, so we have to find the dynamics for ds squared of dgt. And the second part is to find the dynamics of a gt where we have a 2 to power wt. We also have to discuss whether this process is a martingale or it's not. We have also another few exercises related to today's lecture. The first is about this interesting derivative, exotic derivative, we can say, where you have two stocks that are correlated. Yes, the correlation is 70%. And your task is to perform Monte Carlo sampling, Monte Carlo simulation, and compare the solution that you obtain with analytical solution we discussed in the lecture. So please implement the analytical solution and compare to Monte Carlo. And the remaining two are the first one is to improve the Python code which is available on the link in the description of this lecture, and then make it available also for pricing of put options, and make sure that also works for, this is I think, for discount. So I think for purpose, I think not everywhere included interest rate are, so your task is to include interest rate properly, make sure that it works, and extend the pricing to put options. Then another one, the final exercise in slide 24, we have discussed Monte Carlo simulation for this was for the, let's take a look, 24, we have this expression, so we have squared stock, and your task is again to compare analytical expression against the Monte Carlo, the result from Monte Carlo simulation. That basically also would give you a feeling how to, that it really first to confirm that it really works if you didn't believe, and also you will see that really benefits how tremendous difference it is once you apply these measure transformations.